Assalamualaikum and hi, we are from Group 1 and today we will present on blackbody radiation and the Planck distribution, focusing on how thermal radiation explains energy distribution in physics. Blackbody radiation is a fundamental concept in modern physics that describes an idealized object which absorbs all incoming electromagnetic radiations. This problem was successfully explained by Planck's law, which shows that energy is emitted in discrete amounts and that the radiation spectrum depends on the temperature of the body. In this context, photons obey Bose-Einstein statistics due to their quantum nature. For a photon gas, the chemical potential is zero because the total number of photons is not fixed in the thermal equilibrium. As a result, the Bose-Einstein distribution reduces to the Planck distribution, which accurately describes a blackbody radiation. Next, we discuss the non-conservation of photons number. In general, the chemical potential is used to control the total number of particles in a system. However, in a photon gas, photons are massless and can be freely created or destroyed through interactions with all the walls of the container. Because the total number of photons is not conserved, the chemical potential naturally becomes zero. In addition, photons have an integer spin, which classifies them as bosons. As bosons, they obey Bose-Einstein statistic, allowing many identical photons to occupy the same quantum state simultaneously. This bosonic nature is essential in explaining the key features of electromagnetic radiation, such as the high radiation intensity observed at certain frequency in the blackbody spectrum.
Okay, I will be deriving the Planck distribution by treating radiation as a photon gas. Since photons are boson and their number change constantly, we set the chemical potential is equal to zero. This gives us the Bose-Einstein occupancy factor, which tells us how many photons occupy each energy level at the temperature. Next, we calculate the density of state. We look at the standing wave in 3D box and account for two photon polarization. This gives us GV, showing that the number of available slots for energy increase as the frequency squared. To get the final energy density, we simply multiply the energy of one photon HV, the number of states GV, and the occupancy factor. The result is Planck's law. The V power of 3 in the numerator and the exponential in the denominator works together to create the specific shape of blackbody curve. This formula solves the ultraviolet catastrophe because the exponential terms force the energy to drop at a high frequency. These perfectly match what we observe in nature and provide the foundation of the rest of our group analysis.
Next is analyze thermodynamics properties. Thermodynamics quantities of blackbody radiation from the Planck distribution. Blackbody radiation may be regarded as a photon gas in a state of thermobalance. The thermodynamic characteristic of this radiation environment can be obtained from the Planck distribution, which provides the density of spectral energy of radiation within a cavity at a temperature of T. Firstly is Planck distribution. The spectral energy density per unit frequency of blackbody radiation is given by this equation, where h is Planck constant, k is the Boltzmann constant, and c is the speed of light. Second is energy density. The total energy density of blackbody radiation is obtained by integrating the Planck distribution over all frequency, as I shown here. A is the radiation constant. These results show that the energy density of blackbody radiation is increases with the fourth power of temperature, consistent with the Stefan Boltzmann law. The third is radiation pressure. Radiation pressure arises from the moment transfer of photons to the walls of the cavity. For isotropic radiation, the pressure is related to the energy density by this equation. This relation indicates that the blackbody radiation behaves as a relativistic photon gas where the pressure is directly proportional to the energy density. Lastly is entropy density. The entropy density of blackbody radiation can be derived by using the thermodynamic relation for a photon gas with zero chemical potential. This result shows that the entropy density of blackbody radiation scales with the cube of the temperature, reflecting the increasing number of accessible photon states at higher temperature.
Now we have wind displacement law. This law is our primary tool for determine the temperature of distant objects like stars. Just by analyzing their light, it tells us that there is a direct link between an object temperature and the specific wavelength where it emits the most energy. Key takeaway here is the inverse relationship. As an object gets hotter, its peak wavelength gets shorter. This is why a heating element and a stove glows red at first, but hotter stars in the universe appear blue and even ultraviolet. Conversely, cooler objects, including our own body, emit radiation in the longer, invisible infrared spectrum. Mathematically, we express this as lambda equal to B over T by using Wien's constant, which is roughly 2.898 times 10 to the power of negative 3. We can calculate the exact temperature of a body simply by measuring its peak color. Essentially, the bluer the light, the higher the value of T in the denominator. Now we're moving on from the color of light to the amount of energy. We have the Stephan-Boltzmann law. This law tells us that the total energy a black body radiates is proportional to the fourth power of its absolute temperature. Essentially, this means that even a small increase in temperature leads to a massive jump in radiate power. Mathematically, this relationship is derived by integrate the Planck distribution across all frequencies. It proves that the total energy density of radiation increases very rapidly as an object gets hotter. Because of this exponential growth, we use this law to estimate the massive energy output of the star and other complex thermal systems. If we look at the equation, P equals to sigma A T to the power of 4. P is the total power of luminosity. Sigma is the Stephan-Boltzmann constant valued at 5.67 times 10 to the power of negative 8. And A is the surface area and T is absolute temperature in Kelvin. Simply, in this law, temperature is the most powerful factor in determining how much energy an object emits. In stellar physics, we cannot stick a thermometer into a star. We will use Wien's displacement law. This law tells us that the star peak wavelength is inversely proportional to its absolute temperature. Practically, this means hotter stars shift towards shorter wavelength, appearing blue. Cooler stars shift toward longer wavelength, appearing red. As seen in the graph, our sun peaks at 500 nanometer, which places its temperature at roughly 5,800 Kelvin. Next, we use the Stephan-Boltzmann law to determine the star luminosity or its total energy output. The formula is L equals 4 pi r squared. Sigma T to the power of 4 shows that luminosity depends on two factors, the star surface area and its temperature to the fourth power. This explains two key astronomical phenomena. Red giants are incredibly bright because their radii are extremely large, even though their temperatures are low. Conversely, our sun is bright than a red giant, while its temperature is higher. Its smaller radius result in a lower total energy output.
Assalamualaikum, hi, my name is Huda, and today I will explain some real physical application of blackbody radiation, focusing on stellar physics, the cosmic microwave background, and thermal imaging before concluding with the overall significance of this concept. First, the stellar physics. Blackbody radiation is essential for determining the properties of stars. Astronomers use wind displacement law to estimate a star's surface temperature by observing the wavelength at which its emission is maximum. Next, we move to the cosmic microwave background, or CMB, which provides strong evidence for the Big Bang theory. The CMB is the afterglow of the early universe and has vivid and almost perfect blackbody spectrum. Another important application is thermal imaging. All objects emit electromagnetic radiation depending on their temperature. Thermal imaging devices capture this radiation and convert it into temperature map. Unlike visible light, thermal radiation can penetrate smoke, dust, and mist, making it extremely useful. In conclusion, blackbody radiation can be explained using the photon gas model, where electromagnetic radiation is treated as a gas of photon in thermal equilibrium. Since photons are boson and their number is not conserved, they obey Bose-Einstein statistic with a chemical potential equal to 0. This means photons can be created or destroyed freely through interaction with matter in order to maintain thermal equilibrium. This statistical description leads directly to the Planck spectral energy distribution, which successfully explains the observed blackbody spectrum. Overall, blackbody radiation links photon statistics to observable physical laws such as wind displacement law and the Stephen-Boltzmann law. One of the strongest confirmations of this theory is the cosmic microwave background, which preserves the thermal signature of the early universe. Beyond theory, these principles are applied in stellar temperature measurement and the thermal imaging technologies, showing how blackbody radiation connect fundamental physics to real-world observation.
That's all for us. Thank you.